Go outside on a clear night and look toward the south. If the season is right and the planets have aligned in the way they periodically do, you'll see it. A point of light that doesn't twinkle the way stars do, that holds its light steadily, with a reddish tint that sets it apart from everything around it. It's not the brightest object in the night sky. It's not always visible, but when it's there, it's unmistakable. That reddish, steady point. It's a planet, the fourth from the Sun, about half the diameter of Earth, with a thin atmosphere mostly of carbon dioxide, surface temperatures that swing from -125 degrees Celsius in winter to a relatively balmy 20 degrees on a summer afternoon near the equator, dust storms that can cover the entire planet for months, the tallest volcano in the solar system, the longest canyon system anywhere in the solar system, and two small, irregular moons that look like captured asteroids. It's a cold, dry, barren world. The surface is red because the dust contains iron oxide. Rust, essentially. Mars is a rusted planet. Mars is about 225 million kilometers away from Earth on average, though the distance varies considerably as both planets move in their orbits. At its closest approach, when Mars and Earth are on the same side of the Sun and relatively near each other, the distance can shrink to about 55 million kilometers. At its furthest, when Mars is on the opposite side of the Sun from Earth, the distance balloons to about 400 million kilometers. A radio signal from Earth takes between about 3 minutes and 22 minutes to reach Mars, depending on the current geometry. You cannot have a real-time conversation with anyone on Mars. The physics of distance makes it impossible. That distance is part of the story. Everything that has been achieved in Mars exploration has been achieved across that gap. The spacecraft that have reached Mars have traveled for 6 to 9 months through the cold, empty space between the two planets, navigating with extraordinary precision to arrive at a moving target hundreds of millions of kilometers away. The commands that have driven rovers across the Martian surface have crossed that gap at the speed of light, arriving minutes later, and the responses have made the return journey. The pictures of alien landscapes, the chemical analyses of Martian rocks, the sounds of Martian wind, all of it has crossed that gap, a thread of radio waves connecting a small world to a smaller machine on a larger, redder one. And we've been sending things there for over 60 years. Spacecraft, landers, rovers, orbiters. We've crashed things into it by accident and landed things on it with extraordinary precision. We've driven robots across its surface. We've photographed it from orbit so thoroughly that there are maps of Mars more detailed than many maps of Earth's ocean floors. We've listened to the wind there. We've drilled into its soil. We've flown a tiny helicopter in its thin atmosphere. We've looked for signs of water. We've looked for signs of life. We haven't found life. We have, beyond any doubt, found that Mars was once a different world. Warmer, wetter, with a thicker atmosphere, with rivers and lakes, and possibly an ocean covering its northern lowlands. Something happened to Mars, and the story of our attempts to understand what happened is one of the most ambitious and frequently heartbreaking chapters in the history of human exploration. Tonight, we're going to walk through all of it, the entire history of Mars exploration, from the first telescopic observations to the rovers currently driving across the surface right now, while you're settling in, while the night deepens around you. We're going to go slowly. We're going to take our time with the missions that succeeded and with the missions that failed, because there have been many of both, and the failures are as important to the story as the successes. And we're going to try to understand not just what we've found, but why we went, and what we were hoping for, and what it means that we keep going. If you drift off somewhere along the way, That's perfectly fine. Mars will still be there when you wake up, doing what it does, about 225 million kilometers away on average, going about its business in the cold. But if you stay with me, I think you'll find that the history of Mars exploration is one of the best adventure stories in the history of science, full of triumph and loss, full of human ambition and machine resilience, and full of one planet's slow, quiet, extraordinary revelation of its own past. Let's begin. Mars has been known to human beings since before recorded history. In a dark sky without light pollution, Mars, at its closest approach to Earth, is one of the brightest objects visible, outshining everything except the Moon, Venus, and occasionally Jupiter. Ancient Babylonian astronomers tracked its movement through the sky with meticulous care, noting its retrograde motion, the periods when Mars appears to move backward against the background of stars due to Earth overtaking it in its inner orbit. They connected it to their god of war and pestilence, Nergal. The ancient Greeks called it Ares, also their god of war. The Romans named it Mars, their god of war. Almost every ancient culture independently associated this red wandering star with blood and conflict. The color did the work. The Babylonian astronomical records, inscribed on clay tablets and surviving in museums around the world, contain thousands of years of careful observations of Mars and the other planets. The Babylonians were not doing what we would call science, in the modern sense. They were doing something they understood as divination, reading the movements of the sky for signs of what would happen on Earth. But the discipline required to track planetary motions accurately is the same discipline that eventually led to science. Careful observation, systematic recording, pattern recognition, prediction. The Babylonian astronomers could predict the positions of Mars years in advance. They had worked out the mathematical relationships between Mars's cycles and the calendar. In this sense, they were the first Mars scientists, even if they didn't know it. The Chinese called it the fire star. They maintained records of its appearance and disappearance going back thousands of years, and their records have been invaluable to modern historians studying past solar activity and planetary positions. Chinese astronomy was sophisticated and systematically recorded. The imperial court maintained professional astronomers whose job was to track the heavens and report on unusual phenomena. The appearance of a new star, the passage of a comet, the behavior of the planets, all were carefully noted and interpreted. The ancient Egyptians tracked Mars and developed a predictive model of its retrograde motion. They called it Horus of the Horizon and Herdesher, the Red One. The Mayans incorporated Mars into their elaborate calendrical system. They tracked the synodic period of Mars, the time it takes Mars to return to the same position relative to the Sun as seen from Earth, with remarkable accuracy, knowing it was about 780 days. Modern value, 779.94 days. The Mayans were not far off. All of this observation was from a distance. Mars was a point of light, a moving point of light, behaving in ways that careful observers could track and predict, but a point nonetheless. The nature of Mars as a physical world, as a planet with a surface and features and an atmosphere, had to wait for the invention of the telescope. Galileo was the first to observe Mars through a telescope in 1610, and his equipment was too primitive to see any detail. He could tell that it showed phases, like the Moon, confirming it was a sphere illuminated by the sun rather than a self-luminous body. But that was about all. Better telescopes, in the hands of later astronomers, began to reveal more. The Dutch astronomer Christian Huygens, in 1659, produced the first sketch of a surface feature on Mars, a dark triangular region now known as Syrtis Major. a volcanic plain that appears dark because its dust is constantly blown away by wind, exposing darker rock beneath. Huygens also measured the rotation period of Mars by tracking Syrtis Major as it moved across the disk, arriving at a value of about 24 hours, remarkably close to the modern value of 24 hours and 37 minutes. Not bad for a 17th-century telescope pointed at a disk only a few seconds of arc across. In 1666, the Italian-French astronomer Giovanni Cassini, director of the Paris Observatory, observed the polar ice caps of Mars. The bright white patches at the poles, we now know, are made of both water ice and frozen carbon dioxide, dry ice, with the proportions varying with the seasons. Cassini also refined the measurement of Mars's rotation period and observed that Mars moved in a way that allowed a reasonable estimate of its distance from Earth. William Herschel, the German-British astronomer who discovered Uranus in 1781, observed the inclination of Mars's axis of rotation at about 25 degrees, very similar to Earth's axial tilt. He concluded that Mars had seasons, just like Earth. He also observed the polar caps changing with the Martian seasons, and concluded that Mars had an atmosphere, though he vastly overestimated its density. By the 19th century, the disk of Mars could be resolved into a complex patterned surface of light and dark regions. The idea that Mars might be habitable, might actually be home to life, took firm root. The parallels with Earth were tantalizing. Similar rotation period, similar axial tilt, seasonal changes, an atmosphere of some kind, a surface that showed dark regions that some observers hoped might be vegetation. And then came Giovanni Schiaparelli. Schiaparelli was the director of the Brera Observatory in Milan, and in 1877, during a particularly close opposition of Mars when Earth and Mars were unusually close, he made a systematic telescopic survey of the Martian surface and produced detailed maps. He described a network of linear features crossing the bright regions of Mars, which he called canali in Italian. The word means channels or canals, or simply linear features. In Italian, it carried no particular connotation of artificial construction. Irrigation canals and natural river channels were both canali. But when translated into English and other languages, the word became canals. And canals implied builders. The idea of Martian canals captured the public imagination in a way that very few scientific observations have ever done. Newspapers covered it. Intellectuals debated it. The question of whether Mars was inhabited by intelligent beings, perhaps more advanced than humanity, became a topic of serious public discourse. H.G. Wells wrote The War of the Worlds in 1898, imagining what would happen if the Martians, facing the death of their own planet, decided to invade the younger, more vital Earth. The novel is still in print today, and its opening pages, describing Mars as an aging world whose inhabitants look at the Earth with envious eyes, capture the cultural atmosphere of the period precisely. Percival Lowell was the most prominent champion of the canal idea. Lowell was not a professional scientist. He was the son of a wealthy Boston family, a graduate of Harvard, a man who had spent years as a diplomat in Japan and Korea before, in his mid-30s, turning his attention to astronomy. He had the financial independence to pursue the subject on his own terms, and he did so with complete commitment. Lowell built his own observatory in Flagstaff, Arizona, at an altitude of about 2,000 meters, choosing the high-altitude desert of Arizona for its clear, steady air. He moved there in 1894, bought a fine telescope, and began observing Mars. He observed it systematically, drawing what he saw, building up an increasingly detailed picture of the canal network. Lowell believed not just that Mars had canals, but that he understood what they meant. Mars was an old planet, much older than Earth by some theories of the time. Its civilization had advanced far beyond anything on Earth, not because its inhabitants were inherently superior, but because they had had more time. And their greatest engineering achievement was the canal network, a planet-wide irrigation system that pumped water from the polar ice caps to the equatorial cities where the population lived. Mars's deserts were not waste, they were farmland, irrigated by the greatest construction project in the history of the solar system. Lowell wrote 3 books about Mars and gave popular lectures to packed audiences. He made the idea of Martian civilization respectable, or at least respectable enough for widespread public engagement. He was a gifted popularizer, with a poetic and compelling writing style. People wanted to believe what he was saying. The idea of Mars as a living world, of humanity not being alone in the solar system, was deeply attractive. But the scientific community was skeptical from the beginning. The English astronomer E. Walter Maunder and his wife Annie Maunder conducted an experiment in which they showed test subjects photographs of randomly placed dots and asked them to copy what they saw. The subjects, trying to make sense of the random patterns, connected the dots with lines. The experiment suggested that the Martian canals might be a psychological artifact, a product of the human tendency to find patterns and connect random markings into coherent linear features. The astronomer Eugène Michel Antoniadi, using a larger and better telescope than Lowell at the Meudon Observatory near Paris, observed Mars during the 1909 opposition when the planet was again close to Earth. He saw not straight lines but disconnected blotchy patches and irregular features. The canals, he concluded, were an illusion. Better equipment and better seeing conditions revealed a more complex, irregular surface than Lowell's eye and Schiaparelli's had resolved. As photographic techniques improved through the early 20th century, the canals became increasingly difficult to sustain. Photographs didn't show them the way drawings did. The discrepancy between what the eye saw in imperfect conditions, struggling to resolve detail at the limits of resolution, and what a photograph revealed was damning. By the time the space age began in 1957, the scientific consensus had already moved well away from Lowell's interpretation. Most astronomers agreed that the canals were not real features. But the idea of Mars as a potentially habitable world, as a world that might harbor some form of life, however simple, persisted. It was that persistence that drove the early planetary program, and it was Mariner 4's images showing a cratered, apparently dead world that seemed at the time to kill the idea entirely. Until Mariner 9 changed everything again. And then came Giovanni Schiaparelli, the director of the Brera Observatory, the man who drew lines on Mars and changed the course of history. The real revelation of Mars had to wait for spacecraft. The space age began in earnest in 1957, when the Soviet Union launched Sputnik, the first artificial satellite. The beeping signal from that silver sphere, tracked by radio stations around the world, announced a new era in human history. Within months, both superpowers were planning missions to the planets. The Moon came first, but Mars was not far behind in the ambitions of both space programs. The Soviet Union made the first attempts to reach Mars. Between 1960 and 1964, they launched 5 Mars missions, all of which failed. The first 2, Marsnik 1 and Marsnik 2 in 1960, never left Earth orbit because of rocket failures. Mars 1, launched in November 1962, actually made it into deep space. It was on its way to Mars, but lost contact with Earth in March 1963, when it was about 106 million kilometers away, before it reached the planet. Zond 2, launched in 1964, also lost contact before arrival. The scale of the early failure rate is important to appreciate because it sets the context for everything that came after. Getting to Mars required building rockets powerful enough to escape Earth's gravity and send a spacecraft on an 8 to 9 month journey across more than 200 million kilometers of space. It required communication systems that could maintain contact over those distances with the primitive electronics of the 1960s. It required navigation precision that was at the edge of what the era's computers and tracking systems could achieve. And it required that every component work correctly for the entire journey, with no possibility of repair. The Americans had their own failures. The Mariner program was designed to send spacecraft past Mars, Venus, and Mercury. Mariner 3, launched in November 1964, failed when its protective shroud didn't separate properly, weighing down the spacecraft so much it couldn't achieve Mars' trajectory. 3 weeks later, Mariner 4 was launched, and this time it worked. The first spacecraft to actually successfully fly past Mars and return data was the American Mariner 4, in July of 1965. Mariner 4 was a small spacecraft, about 260 kilograms, designed to fly past Mars at a distance of about 9,900 kilometers and photograph its surface. The photographs it returned were a shock. 22 images. In total, 22 grainy, black and white images of the Martian surface. They showed a world that looked nothing like the Mars of Lowell's imagination, or even the relatively benign Mars that many scientists had hoped for. They showed craters, lots of craters. The surface of Mars, as revealed by Mariner 4, looked like the Moon. It was heavily cratered, apparently ancient, geologically dead-seeming. There were no canals. There were no signs of vegetation. There was no sign of anything that looked remotely like the product of biological or geological activity. The images from Mariner 4 arrived not as digital files but as radio signals carrying numerical data that had to be assembled by computer into pictures. The process was slow. While the engineers waited for the computer to process the data, some of them made their own picture by hand. They had strips of paper representing the numbers in each row of pixels, and they colored each strip according to the value, darker for low numbers, lighter for high numbers, and assembled the strips side by side. The first image of Mars was hand-colored by engineers standing at a table in the Jet Propulsion Laboratory using pastel crayons. They held it up and looked at it before the computer had finished its work. It showed craters. The images were also used to estimate the atmospheric pressure at the Martian surface. The result was devastating. The atmosphere of Mars was far thinner than even the most pessimistic estimates, only about 1% of Earth's atmospheric pressure. Liquid water cannot exist at that pressure. It would either freeze or evaporate instantly. Mars, as far as Mariner 4 could tell, was a dry, dead, cratered world, hostile to life in every way. The reaction on Earth was mixed. Scientists were disappointed, but fascinated. The public was deflated. Science fiction writers had spent decades populating Mars with Martian civilizations, dying and otherwise, and those civilizations had now been definitively ruled out by 22 photographs. Mars was not the active world of imagination. It was a dead rock. But Mariner 4 had only seen about 1% of the Martian surface, and the portion it saw, as it turned out later, was one of the oldest, most heavily cratered regions on the planet. Mars was hiding something. The 22 photographs had told one story. the planet had many more to tell. Mariners 6 and 7, which flew past Mars in 1969, confirmed the general picture from Mariner 4, but saw more of the southern hemisphere. They also found evidence of a southern polar cap composed partly of frozen carbon dioxide, confirming the thin atmosphere picture. Mars remained, to all appearances, a world of craters and cold and thin air. And then Mariner 9 arrived and changed everything. Mariner 9 was the first spacecraft to enter orbit around another planet. It arrived at Mars in November of 1971, and it arrived to find a planet completely obscured by dust. A global dust storm, one of the largest ever recorded on Mars, had begun just as Mariner 9 arrived, and for weeks, the entire surface was hidden beneath a blanket of suspended dust particles. The engineers and scientists waited. They kept the spacecraft in orbit, patiently, watching the dust slowly settle. The waiting was its own kind of drama. Mission scientists gathered at JPL in Pasadena, California, watching the orbiter's instruments detect nothing but uniform dust, watching the storm slowly abate. They didn't know what they would find when the dust cleared. They had expectations based on Mariners 6 and 7, which suggested a heavily cratered, dead world. They were about to find out how wrong those expectations were. And when the dust cleared, what Mariner 9 saw transformed our understanding of Mars completely. The first things to emerge from the dust, as they were the tallest features on the planet, were the peaks of enormous volcanoes. The tallest of them, Olympus Mons, rose to a height of about 22 kilometers above the surrounding terrain, nearly 3 times the height of Mount Everest above sea level, and had a base about 600 kilometers across. It was, and remains, the largest volcano in the solar system. The caldera at its summit, the collapsed crater at the top, is about 80 kilometers across and 3 kilometers deep. If you stood at the edge of the caldera, the summit of Olympus Mons, the cliff edge would drop away below you for 3 kilometers, and in the thin Martian atmosphere, you would be technically standing in space, above most of the planet's atmosphere. How did Olympus Mons get so large? On Earth, volcanoes are limited in size by plate tectonics. As the tectonic plate moves over a hotspot in the mantle, the volcano that forms moves away from the hotspot over time, going extinct, while a new volcano forms above the hotspot. The result is chains of volcanic islands, like Hawaii, each one a successively younger volcano, built over the same mantle hotspot. No single volcano gets to keep erupting in the same place for billions of years. But Mars has no plate tectonics. Its crust is a single, stationary plate. When a hotspot forms in the Martian mantle, the volcano above it just keeps growing, erupting, adding material on top of itself for billions of years. Olympus Mons is the result of a volcanic hotspot that operated for perhaps 3 billion years without the crust moving away from it. There were 3 other large volcanoes visible in Mariner 9's images, grouped in a region called the Tharsis Bulge, a vast, elevated region that acts as a planetary-scale geological reference point. The weight of the Tharsis Bulge has actually deformed the shape of Mars itself, creating a bulge visible in the planet's topography and influencing the location of Valles Marineris. Valles Marineris, named after the Mariner program that discovered it, stretched for about 4,000 kilometers along the Martian equator, reaching depths of up to 7 kilometers and widths of up to 200 kilometers. For comparison, the Grand Canyon is about 450 kilometers long, 16 kilometers wide at its widest, and about 1.5 kilometers deep. Valles Marineris would swallow the Grand Canyon as a side tributary, It would stretch from New York to Los Angeles if placed on Earth. The formation of Valles Marineris is still not fully understood. It appears to be a tectonic rift, a place where the Martian crust was pulled apart by stresses associated with the formation of the Tharsis Bulge. The walls of the canyon are thousands of meters of layered rock, encoding hundreds of millions of years of Martian geological history. The canyon is one of the most scientifically compelling regions on Mars and has been studied from orbit with extraordinary attention. Mariner 9 also revealed ancient river channels, branching valley networks that looked unmistakably like they had been carved by flowing water. These were not the artificial canals of Lowell's imagination. They were dried riverbeds, sinuous and branching, the way real rivers branch, carved into ancient terrain over what must have been millions of years. Water, in substantial quantities, had once flowed on the surface of Mars. The picture of Mars that emerged from Mariner 9 was entirely different from the picture of Mariner 4. Mars was not simply a cratered, dead rock. It had enormous volcanoes, suggesting geological activity at some point. It had a canyon that dwarfed anything on Earth. And it had river channels, suggesting that billions of years ago, water had flowed on its surface, liquid water, the stuff of life. The question changed. It was no longer whether Mars might currently harbor life, because the evidence for a living Mars was weak. It was whether Mars might once have harbored life in its warmer, wetter past. And that question drove everything that came next. Let me say something about the people who gathered at JPL to watch the dust storm slowly clear. Some of them were young scientists at the beginning of their careers. Some were established researchers who had already spent years working on Mars. All of them had committed themselves to a planet about which almost nothing was known. They had built a spacecraft and sent it across the solar system on the gamble that it would tell them something worth knowing. When Mariner 9 began revealing what Mars actually looked like, the reaction in the scientific community was a mixture of astonishment and excitement. Everything they had thought they knew about Mars was overturned. The cratered dead world was real, but it was only part of the picture. The dynamic, geologically active, once wet Mars was the other part. Mars was more like Earth than anyone had dared to hope. The scientists who gathered at JPL to watch the dust clear would spend their careers working on what Mariner 9 had revealed. Some of them would go on to propose the Viking biology experiments. Some would work on the global maps. Some would design the first rovers. The Mariner 9 images were the foundation of modern Mars science, the starting point for everything that came after. The Viking program was the direct answer to the question that Mariner 9 had made urgent. If Mars once had liquid water, might it once have had life? And might life, in some form, persist somewhere on Mars today? NASA's Viking program consisted of 2 spacecraft, Viking 1 and Viking 2, each carrying both an orbiter and a lander. They were the most ambitious planetary exploration effort ever undertaken up to that point. The total cost, in today's dollars, would be several billion dollars. The scientific ambition was correspondingly enormous. Viking was not just a geology mission, it was a life detection mission, the first in history. The engineering required to send a spacecraft to Mars, enter orbit, characterize potential landing sites, then detach a lander and successfully deliver it to the surface was at the absolute frontier of what 1970s technology could achieve. Viking's computer systems were extraordinarily primitive by modern standards, but extraordinarily sophisticated for their time. The spacecraft had to be essentially autonomous during the landing sequence, because the communication delay between Earth and Mars meant that ground controllers couldn't react to any problem in real time. The lander had to enter the atmosphere, deploy a heat shield, deploy a parachute, fire retro rockets, and land gently, all by itself, executing a pre-programmed sequence that had been designed months in advance. Viking 1 entered orbit around Mars in June of 1976 and spent about a month searching for a suitable landing site. The scientists were looking for a flat, rock-free area in the northern lowlands. When a site was chosen, the lander separated from the orbiter and descended through the Martian atmosphere. It worked. Viking 1 landed on Mars on July 20th, 1976, 7 years to the day after the Apollo 11 moon landing. The images it returned within minutes of landing showed a rocky surface scattered with boulders of various sizes under a salmon-pink sky. The pink was from iron oxide dust suspended in the thin Martian atmosphere. Mars had a sky, a colored sky. It was alien and yet somehow familiar, a landscape that looked like a desert on Earth, hostile but recognizable. The first images from Mars's surface were assembled by hand, in real time, at the Jet Propulsion Laboratory. They were scanned in column by column, and as each line of the image appeared, the scientists watching could see, for the first time, what the surface of another planet actually looked like at ground level. Some of them had spent their entire careers working toward this moment. When the first complete image appeared, showing the rocky Martian surface and the pink sky, there was reportedly a long silence before anyone spoke. Viking 2 landed on September 3, 1976, at a site in Utopia Planitia, further north than Viking 1. It also returned images and data, including the first images of a Martian winter, when frost formed on the ground around the lander. The landers carried sophisticated instruments, including a meteorology station that measured temperature, pressure, and wind speed through several Martian seasons. But the biology package was what everyone was waiting for. The biology experiments were the most anxiously watched scientific experiments in the history of planetary exploration. There were 3 experiments. The pyrolytic release experiment looked to see whether Martian organisms might be taking up carbon from the atmosphere and incorporating it into organic molecules, as plants do through photosynthesis. The labeled release experiment added a nutrient solution containing radioactive carbon to a Martian soil sample and watched for gases that would indicate metabolic activity. And the gas exchange experiment added water vapor to a soil sample and looked for gases from metabolic processes. The results were confusing and controversial, and they remain somewhat controversial to this day. The labeled release experiment produced a strong positive result. When the nutrient solution was added to the Martian soil, a burst of radioactive gas was released. Exactly what would happen if microorganisms were present and metabolizing the nutrients. The experiment's principal investigator, Gilbert Levin, believed then, and has maintained ever since, that this result indicated the presence of life. He has never wavered from this interpretation. But the other experiments told a more complicated story. The gas exchange experiment produced an unexpected burst of oxygen when water was added to the soil, but chemists concluded this could be explained by reactive chemical compounds in the soil, peroxides or superoxides, without any biological involvement. The pyrolytic release experiment showed some carbon uptake, but not as much as expected from active biological processes. And crucially, the gas chromatograph mass spectrometer, the most sensitive chemical analyzer on the lander, found no evidence of organic molecules in the Martian soil at all. The consensus that emerged, and that most scientists still hold, is that the biology results were produced not by life, but by highly reactive chemical compounds, probably perchlorates, in the Martian soil. The surface of Mars, bombarded by ultraviolet radiation through its thin atmosphere, without the protection of an ozone layer, had become highly oxidizing. Any organic molecules near the surface would be rapidly destroyed. But the question was not entirely closed. Gilbert Levin continued to maintain that life was the simplest explanation for the labeled release result, and subsequent discoveries about the resilience of life on Earth in extreme environments, organisms that live in the dry valleys of Antarctica, in highly acidic hot springs, in the deep crust of the Earth, have kept the possibility of Martian life alive in a way that the 1976 consensus might have seemed to rule out. The debate about the Viking biology results never entirely ended. Viking 1's lander operated until November of 1982, more than 6 years on the Martian surface. Viking 2's lander operated until April of 1980. Together, the Vikings returned more than 50,000 images of Mars and changed our understanding of the planet more profoundly than any mission before or since. After the Vikings, there was a long gap. Political and budgetary priorities shifted. The spectacular results of the Viking program, combined with the negative biology results, seemed to suggest that the basic questions about Mars had been answered. Mars was dry, cold, and apparently lifeless. There were other priorities. NASA turned its attention to the space shuttle, to building the space station, to the outer planets. Mars waited. The Soviets continued trying. They launched a series of Mars missions through the 1970s and 1980s, almost all of which failed. The Mars 2 and Mars 3 landers in 1971 were the first Soviet craft to attempt landing. Mars 2 crashed. Mars 3 landed successfully and began transmitting an image, but failed after only 20 seconds of surface operation, before a complete image could be assembled. The partial image it sent showed only a uniform gray field. The Soviets had been there, briefly, and then lost it. Then, in 1996, came a discovery that reignited Mars excitement in a way nothing had since Viking: a meteorite. The meteorite was named ALH 84001, found in the Allen Hills of Antarctica in 1984. It was a piece of Mars, blasted off the planet by an ancient impact, drifting through space for millions of years, and eventually captured by Earth's gravity. In August 1996, a team of scientists at NASA's Johnson Space Center announced that they had found evidence inside the meteorite of possible ancient microbial life on Mars. They found microscopic structures that resembled fossilized bacteria, organic compounds, magnetite crystals similar to those produced by bacteria on Earth, and carbonate minerals that might have formed in liquid water. The announcement was made at a press conference attended by then-President Bill Clinton, who delivered a brief speech from the White House Rose Garden. "If this discovery is confirmed," he said, "it will surely be one of the most stunning insights into our universe that science has ever uncovered." NASA Administrator Daniel Goldin called it potentially one of the greatest discoveries in the history of science. The scientific community was immediately skeptical, and over the following years, each of the potential biosignatures in ALH 84001 was challenged. The microscopic structures were far too small to be bacteria, as we understand them. The organic compounds could have been terrestrial contamination. The magnetite crystals might have been produced by non-biological processes. The carbonate minerals could have formed at temperatures too high for life. The scientific consensus today is that the evidence for life in ALH 84001 is not convincing, but the announcement had an electrifying effect on Mars exploration planning. The possibility of life on Mars, even ancient microbial life, was back on the agenda. The new wave of Mars exploration began with the Mars Global Surveyor in 1996. Mars Global Surveyor was launched in November 1996 and entered Mars orbit in September 1997. It was the first successful American Mars mission since the Vikings more than 2 decades earlier. It carried a laser altimeter that measured the topography of Mars with unprecedented precision, a camera that could resolve features as small as 1.5 meters across, and instruments to measure the magnetic field, the composition of surface minerals, and the temperature structure of the atmosphere. Mars Global Surveyor operated for nearly 10 years, vastly longer than planned. It mapped essentially the entire surface of Mars. It found evidence of layered sedimentary deposits in the walls of Valles Marineris, suggesting repeated cycles of water deposition over millions of years. It found, most dramatically, features that looked like recent gullies carved into crater walls by liquid water flowing in geologically recent times. And it found, encoded in the ancient magnetized rocks of the oldest Martian crust, the remnant signature of a global magnetic field that had disappeared about 4 billion years ago. Mars Global Surveyor also, famously, finally settled the case of the face on Mars. In 1976, Viking 1's orbiter had photographed the Cydonia region of Mars and captured an image of a landform that looked, at the low resolution available, remarkably like a human face. A broad forehead, eye sockets, a nose, a mouth. The image went viral in the pre-internet sense, being reproduced in newspapers and books, and becoming a staple of UFO and conspiracy literature for decades. Some enthusiasts argued it was an artificial structure, proof of an ancient Martian civilization. NASA scientists said it was a mesa, a natural butte of rock that happened to look face-like due to lighting and the coarse resolution of the image. When Mars Global Surveyor imaged the same area in 1998 and 2001, with its far superior camera, the face looked like exactly what the scientists had always said it was, a natural landform, a mesa shaped by wind and erosion, with no face-like features visible at higher resolution. The light and shadow effect that had made it look like a face at Viking's resolution was simply that, a lighting effect. The face on Mars was not a face. But the story of Mars's possible current water activity was not so easily closed. In the early 2000s, Mars Global Surveyor began finding what looked like fresh gullies on crater walls, features that appeared to be very recent, even geologically current. Could liquid water be flowing on Mars today, in brief episodes, producing these gullies? The debate intensified with the Mars Reconnaissance Orbiter's discovery of features called recurring slope lineae, or RSL, dark streaks that appeared on steep Martian slopes during the warmest parts of the Martian year and faded when temperatures dropped. They appeared to flow downhill, like wet sand or briny water seeping through rock. For a time, they were the most exciting potential evidence for current liquid water on Mars. The debate about RSL continues. More recent analysis suggests that the streaks may be caused by dry granular flows, sand and dust moving, without any liquid water involved. The evidence for a non-water explanation has grown stronger, but the question hasn't been definitively closed. Mars continues to surprise. And the possibility that liquid water, even highly salty, highly concentrated brine, might exist somewhere on Mars today, in brief seasonal episodes, deep underground, or in specific microenvironments, has not been eliminated. Mars Global Surveyor also, famously, finally settled the case of the face on Mars. The face became one of the great cultural curiosities of Mars exploration, a story worth briefly telling. In 1976, Viking 1's orbiter had photographed the Cydonia region of Mars and captured an image of a landform that looked, at the low resolution available, remarkably like a human face. A broad forehead, eye sockets, a nose. The image became a staple of UFO and conspiracy literature for decades. Some enthusiasts argued it was an artificial structure. NASA scientists said it was a mesa, a natural butte of rock that happened to look face-like due to lighting. When Mars Global Surveyor imaged the same area at far higher resolution, the face looked like exactly what the scientists had always said, a natural landform, a mesa shaped by wind and erosion, with no face-like features visible at higher resolution. The lighting effect that had made it look like a face at Viking's resolution was simply that, a lighting effect. The face on Mars was not a face. Mars keeps producing such stories. The recurring slope lineae, dark streaks that appear seasonally on steep slopes, were thought for years to possibly be briny water seeping through rock. More recent analysis suggests dry granular flows. The mystery of Martian methane, detected by Curiosity in seasonal variations, suggests active geology or biology. Mars keeps offering hints and then qualifying them. It is a world that rewards patient attention and resists premature conclusions. The most important things Global Surveyor found were its global map, its discovery of the ancient magnetic field, and its gully features suggesting geologically recent water activity. All of these shaped everything that came after. But alongside Global Surveyor came another mission that embodied a new philosophy. Then, in the mid-1990s, NASA tried a new approach: faster, better, cheaper. Instead of expensive, elaborate spacecraft like the Vikings, the agency would try smaller, cheaper missions that could do less but could fail without catastrophe. Mars Pathfinder landed on July 4, 1997, using a remarkable new system: airbags. The spacecraft was surrounded by enormous inflated airbags before it hit the ground, bounced multiple times across the Martian surface, and rolled to a stop. The airbags deflated, the lander opened, and a small rover, named Sojourner, about the size of a microwave oven and weighing about 10 kilograms, drove down a ramp onto the Martian surface. Pathfinder was not just a scientific mission. It was a public relations triumph. The images it sent back were broadcast on the internet, and the Pathfinder website received an unprecedented 47 million hits in its first month, crashing NASA's servers repeatedly. People around the world were watching a rover drive across another planet in something close to real time. The public fascination with Mars that had defined the Lowell era, which had been dimmed by the Apollo era's focus on the Moon, and then by Viking's ambiguous results, suddenly rekindled. Before we move on, let me tell you what it would feel like to stand on Mars. Because for all the numbers and distances and geological epochs, there is something worth contemplating about Mars as a place, a real place, with its own weather and its own light and its own sounds. If you stood on the Martian surface in a pressurized suit, you would see a landscape that looks, in some ways, like a high desert on Earth. Rocky ground stretching to a horizon that is closer than on Earth, because Mars is smaller and curves away faster. Rocks of various sizes scattered around you, reddish-brown with a coating of iron oxide dust. The sky would be pink during the day, not blue. Pink, from the iron oxide dust suspended in the thin air. At dawn and dusk, the sky near the sun would turn blue, which is the reverse of Earth's sunsets. This is because the dust particles scatter light differently from air molecules. The direct sunlight, filtering through dust, appears blue at low angles. The rest of the sky appears pink. The light would be dimmer than on Earth, about 40% of Earth's sunlight, because Mars is about 1.5 times further from the Sun. Everything would look slightly darker, slightly more amber-tinted. The temperature would be extreme. At the equator on a summer afternoon, it might be a few degrees above 0 Celsius. By midnight, it might be -80. The thin air cannot hold heat. The moment the sun sets, the temperature plunges. And Mars has sounds. Perseverance carries microphones, the first microphones ever sent to Mars, and it has recorded the sounds of the Martian surface. The wind sounds like a high, thin hissing, not the deep roar of an earthly storm, but something more delicate. The laser on Perseverance clicking as it vaporizes rock samples. The remarkably alien sound of Ingenuity flying overhead, its rotors spinning so fast in the thin air that it sounds nothing like any helicopter on Earth. Mars sounds different from any place on Earth. Quieter, thinner. The atmosphere is too sparse to carry sound well, especially at low frequencies. This is the place we've been exploring. Cold and quiet and pink-skied and dusty. A world that once had more noise, more motion, more warmth. A world now patient and still, waiting to be understood. Between 1996 and 2001, both America and Europe launched missions to Mars, with mixed results. In December 1999, the Mars Polar Lander attempted to land near the Martian South Pole. Contact was lost during entry, descent, and landing, and it was never recovered. The likely cause was a software error that caused the engines to shut down prematurely, causing the spacecraft to crash. Alongside the Polar Lander was a small penetrator probe called Deep Space 2, which was designed to punch into the Martian surface and return data from underground. It also failed. The same year, the Mars Climate Orbiter was lost because one engineering team used metric units and another used imperial units, a simple human error that sent the spacecraft on the wrong trajectory into Mars's atmosphere. 2 expensive missions lost in the same year, one to a software bug, one to a unit conversion error. The loss of the Mars Climate Orbiter in particular became a famous cautionary tale in engineering, a reminder that even extraordinarily complex missions can fail for the simplest reasons. The European Space Agency entered Mars exploration in 2003 with its Mars Express orbiter. Mars Express entered orbit in December 2003 and has been returning data ever since, making it the longest-running Mars mission by a non-American agency. It carries radar that has detected subsurface ice. It has imaged the Martian surface in stereo, allowing 3-dimensional maps to be made. And in 2018, its radar detected what appeared to be a subsurface lake of liquid water, or briny water, about 20 kilometers wide and about 1.5 kilometers beneath the surface near the South Pole. The finding has been controversial, with some subsequent studies suggesting it might not be a liquid water lake but some other geological feature. But the possibility remains intriguing. Mars Express also carried the Beagle 2 lander, a British spacecraft designed to land on Mars's surface and search for signs of life. Beagle 2 was named after the HMS Beagle, the ship that carried Charles Darwin on his voyage of discovery. It landed on Mars on Christmas Day 2003, but was never heard from. Years later, the Mars Reconnaissance Orbiter's high-rise camera found Beagle 2 on the surface, its solar panels only partially deployed, which prevented its antenna from operating. It had survived landing, but couldn't communicate. India entered the exclusive club of Mars-capable spacefaring nations in September 2014 when the Mars Orbiter mission, known as Mangalyaan, entered Mars orbit on its first attempt. India became the fourth space agency to reach Mars, and the first to succeed on its maiden attempt. Mangalyaan was remarkable for its cost. The entire mission was completed for about $74 million, less than the production budget of the film Gravity, which was released around the same time. It operated for nearly 8 years, returning images of Mars and studying its surface and atmosphere. India's success demonstrated that Mars exploration was no longer the exclusive domain of the two Cold War superpowers. After the Vikings, there was a long gap. Political and budgetary priorities shifted. The spectacular results of the Viking program, combined with the negative biology results, seemed to suggest that the basic questions about Mars had been answered. Mars waited. 2 rovers, named Spirit and Opportunity, launched in the summer of 2003 and landed on Mars in January 2004. They were larger than Sojourner, about the size of a golf cart, and far more capable. They were each designed to last 90 Martian days, called sols, on the surface. Spirit and Opportunity both landed using the same airbag system as Pathfinder, but in different locations, chosen carefully from orbital data. Spirit landed in Gusev Crater, a large impact crater about 150 kilometers in diameter that orbital imagery suggested might once have held a lake. Opportunity landed in Meridiani Planum, a flat equatorial region where Mars Global Surveyor had detected gray hematite from orbit, a mineral that often forms in the presence of water. Spirit's landing site turned out to be less immediately rewarding than hoped. The crater floor was covered in a volcanic plain that showed no obvious water alteration, but scientists directed Spirit to drive toward the Columbia Hills, about 3 kilometers away. 3 kilometers doesn't sound like much, but for a rover traveling at a maximum of about 50 meters per hour over rugged terrain, requiring painstaking navigation and commands from Earth, it was a significant journey. The Columbia Hills delivered what the crater floor had not. The rocks showed clear evidence of water alteration. Some contained silica, which forms in the presence of water. Some showed chemical alteration from acidic water or steam. Spirit had found its water story, and it was a compelling one. Near a feature called Home Plate, a plateau of layered rock, the chemistry and structure suggested volcanic explosions through water or ice, a violent ancient Mars, where volcanoes had met water in energetic encounters. Spirit eventually got stuck in soft terrain in May 2009, unable to free itself after one of its wheels had long since stopped working. Engineers spent months trying to drive it free. They built a scale model of the situation in a sandbox at JPL, testing every strategy for extraction. Nothing worked. Then the Martian winter reduced Spirit's solar power to the point where it could no longer operate its heaters. Contact was lost in March 2010. Spirit had driven over 7 kilometers. It had climbed hills. It had endured 4 Martian winters. It had photographed sunrises and sunsets across 6 years on the Martian surface. Opportunity's landing site was immediately spectacular. The airbags deposited the rover inside a small impact crater, Eagle Crater, only 22 meters wide. The crater walls exposed layered rocks containing sulfate minerals formed in the presence of water, and the tiny spherical concretions of hematite the mission had been designed to investigate. These concretions, nicknamed blueberries by the science team, though they were gray in color, had formed inside rocks in the presence of acidic water. The water evidence was clear and unambiguous. Mars had once had liquid water here. Opportunity drove and drove. It investigated Eagle Crater thoroughly, then drove out onto the plains to Endurance Crater, then to Victoria Crater, where it spent 2 years examining the beautifully layered sedimentary walls. And then, in 2008, it began the long drive to Endeavour Crater, 22 kilometers away, arriving in 2011 after 3 years of careful driving. The clay minerals in Endeavour's rim told the story of more neutral, more Earth-like water chemistry than anything found before. Mars had layers of history, and Opportunity was reading them one by one. The rover's end came in June 2018, when a massive global dust storm covered the Martian surface in a veil of suspended particles that reduced sunlight to nearly nothing, depleting Opportunity's solar panels. The rover went silent. Engineers sent repeated commands. They sent wake-up calls. They even played songs through the communication link, including Billie Holiday's "I'll Be Seeing You." The rover didn't respond. NASA officially declared the mission ended in February 2019. 15 years and 45 kilometers of Martian terrain after landing. The engineers who worked with Opportunity for those 15 years had invested careers, and in some cases significant portions of their lives, into this machine. The principal investigator, Steve Squires, had spent decades working toward the mission before it even launched. The people who commanded Opportunity's movements every day, who celebrated its discoveries and worried about its problems, and tried to wake it from its final silence, knew it as more than a machine. When it fell silent, many of them cried. The Mars Reconnaissance Orbiter arrived in 2006 and transformed orbital observation of Mars. Its high-rise camera could resolve features as small as 25 centimeters, about the size of a desktop computer, from orbit at about 300 kilometers altitude. It produced images of Mars so detailed that scientists could identify individual boulders, track the movement of sand dunes from year to year, see the tracks left by previous rovers, and study geological features at a level of detail never before possible. Mars Reconnaissance Orbiter is still operating today, still imaging Mars daily, still providing essential data for the mission teams of active surface spacecraft. The Phoenix lander arrived in 2008 and landed in the Martian Arctic. It had a robotic arm that dug trenches in the Martian soil and delivered samples to scientific instruments. Within days of landing, Phoenix made a discovery that had actually been suspected from orbital data, but was dramatic to confirm in person. Just below the surface soil, there was ice. Water ice, dirty with Martian minerals, but water ice. Phoenix watched chunks of the ice sublimate, turning directly from solid to gas in the thin Martian air. Mars had water ice near the surface in its polar regions. The ancient wet Mars that the river channels spoke of was not a complete mystery. The water hadn't all escaped to space. Some of it was still there, frozen, waiting. The Curiosity rover landed in August of 2012 in Gale Crater, a 70-kilometer-wide crater that had a 5-kilometer-tall mountain at its center. The mountain, called Mount Sharp or Aeolus Mons, was made of layered sedimentary rocks, each layer representing a different period in Mars's geological history, a record of climate change and environmental evolution spanning billions of years. Curiosity was designed to climb the mountain and read that record layer by layer, like reading a history book whose pages were made of stone. Curiosity's landing was the most dramatic in planetary history up to that point. The rover weighed about a ton, far too heavy for airbags or conventional retro rockets alone. It used a new system called Sky Crane. The spacecraft entered the atmosphere and slowed with a heat shield that glowed from atmospheric friction. It deployed a parachute, the largest ever used in planetary exploration. Then, in the final seconds, The back shell separated, and a rocket-powered platform called the Sky Crane descended toward the surface, slowing from about 70 meters per second to a hover. Then Curiosity, hanging on cables below the platform, was gently lowered to the surface. The moment its wheels touched, sensors detected the contact, the cables were cut, and the Sky Crane flew away to crash at a safe distance. Mission controllers at the Jet Propulsion Laboratory in California erupted when the signal came through confirming touchdown. The 7 minutes of atmospheric entry had been entirely autonomous, happening across a communication distance that meant nothing could be done about any problem in real time. 7 minutes of terror, the NASA engineers called it. For 7 minutes, everything that was going to happen had already happened. They just didn't know yet if it had gone right. It had gone right. One of the first things Curiosity did after landing was photograph its own wheel tracks in the Martian soil. The tracks were clear, crisp, and included a Morse code message encoded in the pattern of holes in the wheels. The code spelled out JPL for Jet Propulsion Laboratory. The engineers had put their mark on Mars. Curiosity found, early in its mission, clear evidence that Gale Crater had once contained a lake. Not briefly, not during a single dramatic flood event, but persistently, for potentially millions of years. A lake with chemistry that was not highly acidic, not highly alkaline, but relatively neutral, relatively Earth-like. Water in which, by the best assessments of the science team, life as we know it could have existed. Not evidence of life, evidence that the conditions for life had once existed. The specific rock that told this story was called Sheepbed, an ancient mudstone exposed in a place the team named Yellowknife Bay. The mudstone had formed at the bottom of that ancient lake, the fine-grained sediment accumulating slowly over millions of years, preserving the chemistry of the water in its minerals. Curiosity's instruments detected sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon in these rocks. These are the 6 elements most essential for life as we know it. They were all present, in a chemical form, compatible with biological processes. The water that filled this lake billions of years ago was drinkable by human standards. That statement, delivered at a press conference in March 2013, landed quietly but with enormous significance. The water was drinkable, not just wet, not just present, but chemically compatible with life. The question was no longer whether Mars ever had the right chemistry for life. It did. The question was whether anything had taken advantage of that chemistry. Curiosity also found methane in the Martian atmosphere. Methane is interesting because it's unstable in Martian conditions. Ultraviolet radiation and chemical reactions should destroy methane in the atmosphere within a few hundred years. If methane is present, something is producing it now or recently. The methane could be produced by geological processes, by reactions between water and certain minerals, or it could be produced by microorganisms. Curiosity detected seasonal variations in methane levels that suggested an ongoing process, one that was currently active on Mars. This finding, published in 2019, was extraordinary. It didn't prove life. Geological methane production is well understood and is a plausible explanation, but it narrowed the question. Either there was active geology on Mars producing methane, or there was active biology. Either possibility was scientifically significant. As Curiosity climbed Mount Sharp, it read the layered record of the ancient climate change. The lower layers, formed in the lake environment, were rich in clay minerals, indicating relatively neutral pH water and habitable conditions. Higher layers showed sulfate minerals, indicating that the water became more acidic and more saline as the lake began to dry out. Still higher layers showed iron oxides and other minerals consistent with increasingly dry, oxidizing conditions. The mountain was a record of Mars's transition from a wet, potentially habitable world to the dry desert it is today. Layer by layer, Curiosity was reading that transition, and the picture that emerged was detailed, complex, and spanning hundreds of millions of years. Curiosity has been operating on Mars for more than 12 years now. It has driven over 30 kilometers, much of it up the slopes of Mount Sharp, reading the geological record layer by layer. It has found evidence of a Mars that transitioned, over hundreds of millions of years, from a warm, wet world with lakes and rivers to a cold, dry world with only occasional liquid water, to the frozen desert it is today. In February of 2021, 3 spacecraft arrived at Mars within days of each other, reflecting a launch window in July 2020 that multiple countries had used simultaneously. The UAE's Hope orbiter became the first Arab interplanetary mission when it successfully entered Mars orbit on February 9, 2021. The mission was remarkable, not just scientifically, but politically. The UAE had no prior history of deep space exploration. It hired international experts, partnered with the University of Colorado Boulder to develop the spacecraft, and trained a generation of Emirati engineers and scientists on the project. The mission was intended to signal the UAE's ambition to become a knowledge-based economy, capable of high-technology achievement. Hope carries instruments to study the Martian atmosphere and climate, and it has been returning comprehensive data on the Martian weather, building the first complete picture of how the Martian atmosphere behaves across an entire Martian year. China's Tianwen-1 mission entered Mars orbit on February 10, 2021. It was China's first independent Mars mission, following a Chinese instrument that had flown on a Russian spacecraft in 2011 and never reached Mars when the Russian spacecraft failed. Tianwen-1 was ambitious in scope: an orbiter, a lander, and a rover, all in one mission, a combination that no other country had attempted on a first Mars mission. On May 22, 2021, the Zhurong rover successfully landed in Utopia Planitia and drove onto the Martian surface. China became only the second country, after the United States, to successfully operate a rover on Mars. The rover's name means fire god in Chinese mythology. Zhurong found evidence of ancient flooding in the Utopia Planitia basin and detected layered subsurface deposits with its ground-penetrating radar, adding to the growing picture of Mars's watery past. And on February 18, 2021, NASA's Perseverance rover landed in Jezero crater in the most complex and high-stakes landing sequence ever attempted on Mars. Perseverance's landing system, a refined version of Curiosity's sky crane, had been improved and tested exhaustively. But nothing completely eliminates the tension of those 7 minutes of autonomous entry, descent, and landing, when the spacecraft is on its own, making decisions at speeds that Earth cannot influence. Perseverance landed safely. The images it returned from Jezero crater showed a landscape of ancient lake sediments and the preserved delta of a river that had once flowed into the crater from the west, depositing its load of sediment layer by layer over millions of years. Jezero crater had been chosen precisely because it was one of the most compelling potential sites for ancient life on Mars. A lake with a river delta, the kind of environment where, on Earth, sediments carry and preserve biosignatures, chemical and physical signs of biological activity. Perseverance's instrument suite was the most sophisticated ever sent to another planet. Its Sherlock instrument used deep ultraviolet Raman spectroscopy and fluorescence to look for organic compounds and potential biosignatures. Its pixel instrument used X-ray fluorescence to characterize the elemental and mineral composition of rocks at fine scales. Its MOXIE instrument demonstrated the production of oxygen from Martian carbon dioxide, a critical step toward future human missions. Its microphones recorded sounds on Mars for the first time, including the sounds of the thin Martian wind and the crackling of a laser vaporizing rock samples. But Perseverance carried something else that had never flown to another planet before. Strapped to its belly during the landing sequence and deployed on the Martian surface in the first weeks after landing was a small helicopter, Ingenuity. Ingenuity was a technology demonstration, a proof of concept for powered flight in the thin Martian atmosphere, where the air pressure is less than 1% of Earth's. To fly in that thin air, Ingenuity's contra-rotating rotors had to spin at about 2,500 revolutions per minute, far faster than any helicopter on Earth, to generate enough lift with the sparse air molecules. The body was incredibly lightweight, constructed of carbon fiber and foam. It weighed only about 1.8 kilograms. Its solar panel charged a small lithium-ion battery. Everything about it was pushed to the minimum possible weight while maintaining function. The Mars helicopter concept had been proposed by engineers at JPL for years, and it had been rejected repeatedly as too risky, too complex, too likely to fail. Flight in Martian air was genuinely uncertain. The theoretical models said it should work, but theory and practice are not always the same. No one knew for certain that it would fly until it flew. On April 19, 2021, Ingenuity made its first flight. It rose to an altitude of 3 meters, hovered for 30 seconds, and landed. The flight lasted 39 seconds in total. It was the first powered, controlled flight by an aircraft on another planet in the history of humanity. Mission controllers at JPL watched, waited, and then erupted when the data came back confirming the flight. Mimi Ong, the project manager for Ingenuity, had tears streaming down her face. She had fought for years to get the helicopter approved and built and flown. She had argued for it in meetings, defended it in reviews, championed it against skepticism from every direction. And now it had flown on Mars. There's a small piece of cloth attached to Ingenuity, a tiny square of fabric taken from the wing of the Wright brothers' flyer, the aircraft that made the first powered, controlled flight on Earth, on December 17, 1903, at Kitty Hawk, North Carolina. It's a connection across 118 years and hundreds of millions of kilometers between the first flight on one world and the first flight on another. Ingenuity flew again and again. The 5 planned demonstration flights stretched to 10, then 20, then 50. By early 2024, it had completed more than 70 flights, covering more than 17 kilometers of Martian airspace, reaching heights of 24 meters, traveling at speeds up to 10 meters per second. It had provided aerial reconnaissance of terrain that would take Perseverance weeks to drive to, scouting routes and identifying scientific targets. It had transformed our understanding of what aerial exploration of Mars could look like. In January 2024, Ingenuity's rotors were damaged during a hard landing, and it could no longer fly. The helicopter was retired where it had last landed. Its mission ended, its place in history secured. It had been designed for 5 flights, lasting about 30 days. It completed 72 flights over nearly 3 years. Perseverance, meanwhile, has been methodically doing science in Jezero Crater and beyond. It has drilled into and collected samples from a variety of rocks, sealing them into titanium tubes and either storing them on board or leaving them at carefully designated depot sites for future retrieval. These samples are Mars's most compelling secrets, preserved in the most scientifically promising rocks the science team could find, sealed and waiting. The plan is for a Mars sample return mission, a joint project between NASA and the European Space Agency, to collect these samples and return them to Earth. The mission design involves a lander that carries a small rocket, called the Mars Ascent Vehicle, and a robotic arm that can collect the tubes from the depot. The Mars Ascent Vehicle will launch the samples into Mars orbit, where an orbiter will capture them and return them to Earth. The samples would land in a capsule similar to the ones used to return comet material and solar wind from NASA's earlier sample return missions. If it works, it will be the first time material from Mars has been returned to Earth. The samples will be analyzed in sophisticated Earth laboratories that can look for biosignatures with tools and techniques far beyond anything that can be sent to Mars. The results of those analyses may finally answer the question of whether Mars ever hosted life, or they may add further complexity, further ambiguity, to a question that has been asked since Lowell looked through his telescope and saw what he hoped to see. In February of 2021, 3 spacecraft arrived at Mars within days of each other. Let me slow down for a moment and tell you more about what Mars is before we continue the exploration story, because the planet itself is worth knowing better. Mars formed about 4.5 billion years ago, at the same time as the rest of the solar system, from the same disk of gas and dust that formed the Sun, Earth, and everything else. Mars formed further from the Sun than Earth, in a cooler region of the disk, and it formed with less mass. Why Mars is so much smaller than Earth is actually an interesting question. The giant planet Jupiter, early in the solar system's history, appears to have disrupted the region between the current orbits of Mars and the asteroid belt, preventing the material there from assembling into a larger planet. Mars may have been a normal-sized planet in the making that was starved of the material it needed to grow. In its first billion years or so, Mars was a very different world from what it is today. This early period, called the Noachian period by geologists studying Mars, after Noah's Ark, was Mars's wet epoch. Geological evidence from multiple missions, both orbiters and rovers, shows that Mars had liquid water on its surface during this period. Rivers carved valleys, lakes filled impact craters. The northern lowlands may have held an ancient ocean, though the evidence for this is still debated. A thick atmosphere, probably dominated by carbon dioxide with some nitrogen and other gases, produced a greenhouse effect strong enough to keep average temperatures above freezing, despite the weaker sunlight at Mars's greater distance from the Sun. And then something changed. The change was not sudden, on geological timescales. It happened over hundreds of millions of years. But the outcome was clear. Mars lost its thick atmosphere, lost its liquid water, and became the cold desert it is today. The key was the magnetic field. Mars, in its early history, had a global magnetic field generated by convection in its liquid iron core, similar to the magnetic field that currently protects Earth. This magnetic field deflected the solar wind, the stream of charged particles flowing outward from the Sun that would otherwise strip away the atmosphere. But Mars's core, smaller than Earth's, cooled more rapidly. As it cooled, the dynamo stopped. The magnetic field disappeared about 4 billion years ago, leaving Mars's atmosphere unprotected. The solar wind then slowly eroded the atmosphere, not quickly, not dramatically, but steadily. Over billions of years, the solar wind stripped atmospheric gases into space. The atmosphere thinned, the greenhouse effect weakened, temperatures dropped. Water that had been liquid froze. Some water ice was sequestered in the polar ice caps and underground. Some water was chemically bound into minerals in the surface rocks, the hydrated minerals that the rovers have been finding. And some water was broken apart by ultraviolet radiation, the hydrogen escaping to space and the oxygen remaining behind, reacting with iron-rich surface rocks to produce the iron oxides, the rust, that gives Mars its red color. Today, Mars's atmosphere is about 95% carbon dioxide, with small amounts of nitrogen, argon, and trace gases. The surface pressure is about 6 millibars, less than 1% of Earth's sea level pressure. Water cannot exist as a stable liquid at this pressure, except in highly concentrated brines at very low temperatures. Liquid water is essentially absent from the Martian surface today, though it might persist in certain special conditions. MAVEN, the Mars Atmosphere and Volatile Evolution spacecraft, launched in 2013 and arriving at Mars in 2014, has been studying the process of atmospheric loss in detail. By measuring the rate at which the solar wind strips gases from the upper Martian atmosphere today, and by reconstructing historical solar activity, MAVEN has confirmed that Mars has lost the equivalent of an atmosphere several times denser than the current one to solar wind erosion over the past 4 billion years. The story the geology tells and the story the atmosphere tells are consistent. Mars lost its magnetic field, then lost its atmosphere, then lost its surface water, then became the frozen desert we see today. Understanding this history is important not just for understanding Mars, but for understanding planetary habitability in general. Earth has maintained its magnetic field, its thick atmosphere, and its liquid water because it is larger, its core is still warm, and its magnetic dynamo is still running. If Earth ever loses its magnetic field, it too will slowly lose its atmosphere. The story of Mars is a cautionary tale about the long-term habitability of rocky planets, a story that planetary scientists study with profound attention. Let me also tell you about Mars's moons, because they're part of the picture, and they're extraordinary in their own right. Mars has 2 moons, Phobos and Deimos, discovered in 1877 by Asaph Hall, an American astronomer, using the Large Telescope at the U.S. Naval Observatory in Washington. Hall found them in the same year Schiaparelli drew his Canali, during the close approach of 1877. Hall had nearly given up the search when his wife Angelina encouraged him to keep trying for one more night. He found Deimos on August 12th and Phobos on August 17th. Both moons are tiny. Phobos is the larger, only about 27 kilometers across at its widest. Deimos is only about 15 kilometers. They're irregular, potato-shaped lumps, covered in craters, more like asteroids than the round moons we imagine. The leading theory is that they are captured asteroids, rocks from the asteroid belt captured by Mars's gravity long ago. Phobos orbits Mars at a distance of only about 9,000 kilometers, closer than any other moon orbits its parent planet. It orbits faster than Mars rotates. Phobos completes its orbit in about 7 hours and 39 minutes. From the surface of Mars, Phobos would rise in the west and set in the east, twice each Martian day. Phobos is also spiraling inward toward Mars. In about 30 to 50 million years, tidal forces will tear it apart, creating a ring of debris around Mars. Japan is planning a mission called Martian Moons E-Exploration, or MMX, intended to land on Phobos, collect samples, and return them to Earth, possibly helping determine once and for all whether the moons are captured asteroids or remnants of a giant impact that once struck Mars. In 60 years of Mars exploration, we have gone from the first grainy flyby images that showed a dead, cratered world, to the knowledge that Mars once had a warm, wet climate, with rivers, lakes, and possibly an ocean, with a thicker atmosphere, protected by a magnetic field, with organic chemistry, with conditions in which life as we know it could have existed. We have gone from 22 photographs to billions of images. We have gone from knowing essentially nothing about the Martian surface to having detailed maps of the entire planet at extraordinary resolution. We have not found life. That has to be said clearly. No mission has found definitive evidence of life on Mars, past or present. The question remains open. But the conditions for life existed. That is established. Whether life actually arose in those conditions is the question that drives every mission that goes to Mars now, and every mission that will go in the years to come. Let me say something about why that question matters so much. Because it's worth slowing down to think about it. If we find evidence of life on Mars, any kind of life, even the most primitive microbial life preserved in ancient rocks, it would be one of the most transformative discoveries in the history of science. It would mean that life arose independently on two planets in the same solar system. And if life can arise independently twice in the same solar system, the implication is profound. Life is probably not a rare accident. It is probably something the universe does wherever conditions permit. The universe would be teeming with life in other solar systems, around other stars, throughout the galaxy. The philosopher and cosmologist Brandon Carter coined the term the anthropic principle to describe the observation that we find ourselves in a universe compatible with our existence. But there's a deeper question underlying that observation. How easily does the universe produce life? If Mars once had the conditions for life, and life arose, the answer is easily. The universe produces life readily. We are not alone, and probably never were. If, on the other hand, Mars had all the conditions for life, liquid water, organic chemistry, moderate temperatures, billions of years of time, and life never arose, that would be a different kind of transformative discovery. It would suggest that life is much harder to get started than we thought. That conditions alone are not enough. That there is something else required, something we don't understand, some additional step that Earth accomplished and Mars didn't. And that would mean life might be genuinely rare in the universe. Earth might be extraordinary. We might, in fact, be alone, or nearly so. Either answer matters more than almost anything else science could discover. Either answer transforms our understanding of our place in the cosmos. The first answer would tell us that the universe is full of life and that we are one instance among billions. The second would tell us that we are something extraordinary, perhaps unique, perhaps cosmically valuable in a way that is almost too large to hold in the mind. And we're looking, carefully, methodically, with every instrument we can design and launch and land and drive. We're reading the rocks. We're analyzing the soil. We're studying the ancient chemistry preserved in Martian sediments. We're building sample return missions. We're planning human expeditions. We're trying, with every tool available to us, to answer this question. The story isn't over. It's barely begun, in the timescale of scientific understanding. The next chapter of Mars exploration, the chapter being written right now, involves human beings. Not yet. But the planning is real, the technology development is real, and the timelines, while uncertain, are not impossibly far off. SpaceX has developed the Starship rocket specifically with Mars in mind. Starship is a fully reusable spacecraft, designed to be refueled in Earth orbit and then sent on a trajectory to Mars, carrying crews and large amounts of equipment. Its payload capacity to Mars is designed to be on the order of 100 tons or more, vastly more than any rocket that has ever flown to Mars. Elon Musk, the founder of SpaceX, has spoken extensively about his desire to establish a self-sustaining city on Mars within his lifetime, a goal that most space analysts consider extremely optimistic in its timeline, but not impossible in principle. NASA's Human Mars program is more methodical and, at least as of the mid-2020s, less well-funded than SpaceX's ambitions. NASA has been developing the Space Launch System rocket and the Orion crew capsule, which are intended to take humans back to the moon first, in the Artemis program. A crewed moon landing was the intermediate step before Mars. The moon serves as a testbed for the technologies and procedures needed for long-duration deep space missions, within a distance from Earth that allows emergency return. Going to Mars is categorically harder than going to the moon. The moon is 3 days away. In an emergency, astronauts on the moon could potentially be returned to Earth within days. Mars is, at best, 6 months away, and usually more than that. During the time when Earth and Mars are in the worst orbital configuration, a crew on Mars would be there for at least 2 years, regardless of any emergency, because the launch windows back to Earth only open at specific times. A crew that goes to Mars is committed for approximately 2 to 3 years of total mission duration. The radiation environment during that 2 to 3 years is a serious concern. In deep space, away from Earth's protective magnetic field, astronauts are exposed to galactic cosmic rays and, during solar events, intense bursts of solar energetic particles. The radiation dose during a Mars mission would be roughly equivalent to having a CT scan every 5 to 6 days for 2 years. This is a known cancer risk. Solutions include heavier shielding, which adds mass and cost, and the possibility of finding or creating habitats on Mars that use Martian soil as radiation shielding. Life underground on Mars would be far better shielded from radiation than life on the surface. The thin Martian atmosphere and lack of an ozone layer also mean that the surface of Mars is sterilized by ultraviolet radiation to a depth of a few millimeters. Any microorganisms on the surface would be quickly killed by UV. This is part of why the Viking biology experiments produced the chemical reactions they did, and part of why future Mars missions looking for life focus on the subsurface. Life on Mars, if it exists, is almost certainly underground, where radiation doesn't reach, and where water ice might persist as liquid at certain depths. Food production on Mars would eventually need to be local. Shipping food from Earth is expensive and slow, limited to the regular launch windows every 26 months, when Earth and Mars align favorably. A self-sustaining Mars colony would need to grow food, probably in pressurized greenhouses, using Martian soil, supplemented with nutrients and water, extracted from ice. The MOXIE instrument on Perseverance demonstrated one piece of this puzzle, making oxygen from Martian carbon dioxide. If you can make oxygen, you can sustain plant growth. If you can grow plants, you can sustain human life. Water is another key resource. Mars has water ice at the poles and likely in the subsurface at a range of latitudes. The MOXIE oxygen production also requires water as a starting material. Future missions will need to identify accessible water ice and develop methods to extract and purify it. Some proposed landing sites for human missions have been chosen partly for their proximity to accessible ice deposits. The psychological dimension of a Mars mission is not trivial. 2 to 3 years in a confined space, with a crew of perhaps 6 people, separated from Earth by a communication delay of up to 24 minutes one way. No opportunity to call home and hear a voice respond for 48 minutes. No possibility of a rescue mission in any reasonable time frame. The psychological demands on the crew would be extraordinary. Space agencies have studied the psychology of long-duration spaceflight extensively, through missions on the International Space Station, through analog missions in Antarctica and in underwater habitats, and through the psychological research that has followed crews through the ISS experience. And yet, people want to go. The Mars community, the scientists and engineers and enthusiasts who follow Mars exploration, includes many people who would willingly sign up for a Mars mission if one were offered. The vision of standing on the surface of another planet, of looking up at the sky of another world, of being part of the first human footsteps on Mars, is compelling enough that many people would accept the risks and the duration and the psychological demands. Whether it happens in the 2030s, as some optimists project, or the 2040s, or later, it will happen. The trajectory of Mars exploration is toward that moment. Every rover that drives across the Martian surface is learning what it's like to operate there. Every orbiter is finding potential landing sites and characterizing the resources available. Every biology experiment is refining our understanding of what will and won't be found. The machines are paving the way. But none of these challenges is insurmountable in principle. People are working on all of them. The technical problems of getting to Mars and surviving there are being addressed with the same methodical engineering that addressed the problems of getting to the Moon and landing there. Let me slow down now and let all of this settle. You've traveled quite a distance tonight. From the ancient Babylonians watching a red point move against the stars, to Huygens sketching Syrtis Major through his telescope, to Schiaparelli drawing his canali, to Lowell building his observatory in Arizona to study the irrigation systems of a dying civilization that didn't exist, to Mariner 4's 22 photographs and their cold, cratered revelation. From Vikings' biology experiments and their ambiguous results, to Pathfinder's bouncing airbags and tiny rover, to Spirit and Opportunity driving across the red plains and climbing into the hills, to Curiosity's nuclear-powered laboratory and its ancient lakebed, to Ingenuity hovering in alien air, to Perseverance collecting its sample tubes in Jezero crater, waiting for a future mission to collect them and bring them home. It's a long story, a story that spans 60 years of human effort and spans the entire history of Mars itself, 4.5 billion years of planetary evolution, a story of ambition and loss and patience and occasional, extraordinary triumph. Let me dwell for a moment on what those triumphs actually mean, because it's easy, when you read a list of mission accomplishments, to let the numbers wash over you without feeling their weight. Think about what it takes to land a spacecraft on Mars. You build it on Earth, in a clean room, carefully, over years, testing every component, every circuit, every weld. You put it on a rocket and launch it, hoping the rocket works, hoping the trajectory is right, knowing that any error of even a few thousandths of a degree in the launch direction will accumulate over hundreds of millions of kilometers into a miss. You track it through space for 6 to 9 months, making tiny trajectory corrections to keep it on target, and then, as it approaches Mars, you hand control over to its onboard computer, because the communication delay means you can't react in real time. You watch the telemetry on your screens, and you wait. During the entry, the spacecraft is falling toward Mars at several kilometers per second. The heat shield glows. Temperatures reach hundreds of degrees. Then the parachute deploys, in air too thin for parachutes to work as well as they do on Earth. Then the retro rockets fire. Then, for the landing systems that have been used in recent missions, the sky crane, or the airbags, or some other extraordinary contrivance, delivers the spacecraft to the surface. And then, a signal comes back, at the speed of light, 8 minutes later, telling you whether it worked. It has worked many times. It has failed many times. Every time it works, it represents years of effort by hundreds or thousands of people. Every time it fails, those years of effort and the aspirations they embodied vanish in a moment of silence from deep space. The people who do this work are remarkable. They are engineers and scientists and project managers and technicians, people who have dedicated significant portions of their lives to the project of understanding another world. Many of them have worked on Mars missions for decades. They know the rovers not just as machines, but as the product of their best thinking, their problem-solving, their late nights and early mornings, and the particular kind of concentrated attention that only matters to you when the stakes are high enough. When opportunity fell silent in June 2018, and the NASA engineers spent months trying to wake it, and finally accepted that it was gone, the grief in the mission control room was real. Not theatrical grief, not performed emotion for the cameras. Real grief, the kind you feel when you lose something that has been part of your daily life for 15 years. Something you have cared for and worried about and celebrated with and argued over. The rovers become, in some deep sense, proxies for human curiosity. They go where we cannot go. They see what we cannot see. They bring back, in the form of data and images, a piece of a world that is otherwise unreachable. And the people who build them and operate them invest in them something of themselves, something of their own need to understand. There's something profound about that investment, about the human need to know, about the willingness to spend years and resources and ingenuity on the question of whether another planet once harbored life, or whether it harbors life now, or whether it might one day harbor human life. There's no obvious practical return on investment in Mars exploration. Not yet, not in any immediate sense. We're not mining Mars. We're not selling what we find there. We're spending enormous resources on a question, the oldest kind of question. What is out there? And are we alone? This is one of the defining characteristics of our species. We want to know. We build instruments to look further, to hear frequencies beyond our range, to detect particles that pass through us without any normal interaction. We send machines to places we cannot go. We ask questions that will take generations to answer, and we begin the work of answering them anyway, because the asking itself matters. Mars is out there right now, in the dark. Perseverance is sitting on the surface of Zhurong crater, its instruments quietly monitoring, its sample tubes in their depot, waiting. The Mars Reconnaissance Orbiter is passing overhead, imaging the surface, relaying data. Curiosity is somewhere on the slopes of Mount Sharp, its nuclear generator keeping it warm through the cold Martian night. What is the temperature on Mars right now, tonight? It depends on where on Mars we're talking about and what season it is. At the equator, temperatures might be somewhere around -20 degrees Celsius after sunset, dropping to -80 or 90 degrees before dawn. In the polar regions, it's colder still. The thin atmosphere offers almost no thermal blanket. Mars loses heat rapidly to space after sunset. It's a cold world, a quiet world, a world without cities or roads or the sounds of animals or the smell of water on stone or any of the 10,000 things we associate with living planets. Except that it once had some of those things. Rivers flowed there. Lakes accumulated sediment there. The conditions for life existed, and the question of whether life arose in those conditions is still open. Maybe it did. Maybe microorganisms once lived in the lakes of ancient Mars, billions of years ago, swimming in the water that carved those river valleys. Maybe they adapted as the climate changed, retreating underground as the surface dried out, finding niches in the rock where liquid water still persisted. Maybe they survive today, somewhere deep underground, far below the reach of our instruments so far, metabolizing slowly in the dark. Maybe they didn't. Maybe Mars had everything life needed except the spark, whatever it is that transforms chemistry into biology. Maybe the conditions were right and life just never happened, for reasons we don't understand. Maybe life is rarer than we hope, requiring not just the right environment but something else, something we haven't identified. Either answer matters enormously. Either answer transforms our understanding of the universe and our place in it. And we're still looking, with everything we have. With every clever instrument we can design, and every rocket we can build, and every engineer willing to spend their working life on this question. Think about that, quietly, as your thoughts slow. Somewhere out there, in the cold and the dark, our machines are working on our behalf, looking for answers to the oldest questions. Patient and methodical and extraordinarily capable, in the way that human ingenuity expressed in machines can be. Mars is quiet tonight. The wind may be blowing across Zhurong crater, lifting dust from the ancient lakebed, carrying it briefly airborne before it settles again. The two moons, tiny Phobos and smaller Deimos, are moving across the Martian sky in their irregular orbits. The sun has set on the side of Mars where our rovers are parked, and they're in low power mode, waiting for morning. And we, here on Earth, are also settling toward the quiet of sleep. Billions of kilometers away from our machines, separated from them by the speed of light, connected to them only by the intermittent radio signals that link us to our furthest extensions. Sleep is, in a small way, a kind of intermission in the exploration. The scientists who work on Mars missions don't stop working when they sleep, not exactly. The Mars day is 37 minutes longer than the Earth day, which means that over time, a Martian sol and a terrestrial day drift in and out of alignment. Mission teams have, in the past, shifted their working hours to match the Martian day, getting up and going to sleep according to Mars's clock rather than Earth's. This is disorienting for families and friends, but allows the team to be available during the Martian daytime when the rovers are active. The commitment is total. Mars becomes, for the people who work on these missions, not just a workplace, but a presence in their lives. They think in Martian sols. They plan their weeks around orbital mechanics. They know the weather on another planet. They have colleagues who are machines on another world. Let the images drift. The pink sky of Mars in Viking's first photographs, the blueberries of Opportunity's landing site, the silhouette of Curiosity against the Martian horizon, Ingenuity lifting off the red dust, its rotors blurring in the thin air, hovering for the first time in the history of aviation on another world. The titanium sample tubes of Perseverance, sealed and waiting in Zhurong crater. And somewhere in the dark tonight, Mars. That reddish point of light in the night sky, if you know where to look, if the season is right. Patient and cold, and full of secrets it hasn't finished telling us. The story of Mars exploration is not over. It is, in some sense, only beginning. The missions of the next few decades will answer questions that the missions of the last 60 years have made possible to ask. Whether there is or was life on Mars. What exactly happened to turn a warm, wet world into a frozen desert? Whether human beings can survive there. Whether our species will one day stand on the surface of that red world and look up at a sky that is alien but somehow comprehensible, with the Earth visible as a pale blue dot in the Martian morning sky. These are questions for the future. They will be answered, or not, by people who are children now, or not yet born, by missions that haven't been proposed yet, using technologies that haven't been invented yet, informed by science that hasn't been done yet. The exploration of Mars is a multi-generational project, like the building of a cathedral, with each generation adding its work to the work of those who came before. But right now, tonight, the foundation is solid. 60 years of missions, hundreds of thousands of images, the knowledge that Mars was once habitable, the samples waiting in their titanium tubes, the orbiters circling overhead, the rovers parked in the Martian night. Sleep well. The rovers are working. The orbiters are circling. The scientists are studying the data. The engineers are planning the next mission. The story of Mars exploration continues, whether you're awake to watch it or not. And tomorrow, if the sky is clear and the season is right, go outside after sunset and look south. Find the reddish point that doesn't twinkle. Think about what it is. A planet half the size of Earth, cold and dry and dusty, where our machines are doing our work for us, where the answers to the oldest questions might be waiting in the ancient mudstones of a dried lake bed, or in the subsurface ice of the polar regions, or somewhere we haven't looked yet. It's close enough that ancient peoples saw it every night and named it after gods. Close enough that its light takes only 3 to 22 minutes to reach us, depending on the orbital geometry. Close enough that we've sent dozens of machines there, and some of them are still running. And far enough that every mission takes 6 to 9 months to complete the crossing. Far enough that a human crew would be committed for 2 to 3 years. Far enough that each photon of data from a Martian rover represents a journey of millions of kilometers just to reach us. Both things are true. Both things are extraordinary. Mars is out there right now, in the dark, being exactly what it is. A rusted, cold, quiet world with an extraordinary past and an uncertain future. A world we have been trying to understand for 60 years and will keep trying to understand for generations more. A world that may hold the most important answer science has ever sought. Rest well. There is so much left to learn, and we're still going. Sleep well.